Hi, my name is Nai Wu, and today we're looking at Lab 5 Magnetic Braking with Faraday. So for the introduction, the objective of this lab is to collect data from a magnet falling through an aluminum foil tube. And it's also to create a computational model of the interactions between the tube and the magnet, and to compare its results to the observational data. Concepts we'll learn during this lab include the magnetic flux, Faraday's law, Lenz's law, magnetic force. And then I just played the video, but to your right was the video that we did during the experimental part. So formulas that we use include Faraday's law, the magnetic field of a dipole, the EMF created by a moving dipole, and the magnetic force on a wire. So for procedures and data results, so first we need to determine where north is on the magnet and label it. Secondly, we need to hold the tube vertically and position the magnet right above the opening of the tube. Third, we are going to record the tube while the magnet drops, and the entire tube must be in frame. Fourth, in a video player, we're going to find the time code where the magnet enters and exits the tube. And then 5, we're going to repeat this 5 times and then calculate the average time. Um, we end up measuring the dimensions of the tube, so 30 centimeters in length, 0.5 centimeters for the width of the foil, and 1.2 centimeters for the inner radius. The magnitude of the magnetic dipole moment was 2.24, and the mass of the magnet was 0.024. Our average time at the end was 1.83 seconds. So the computational model. This first part is the physical constants. The second part is the dimensions of the tube. This third one is the function to calculate the B field of a bar magnet, while this fourth one is the rate of change in the magnetic flux through a ring. And this tiny little one right here is the current induced in each ring. This next code is the force exerted on each current ring, and then this little code right here is the forces acting on the magnet while falling through the tube, which is the gravitational and the magnetic field. And then last but not least, this code is the updating position and velocity of the falling magnet. And then at the end, this is what the code spits out. We got a little graph and we have a little diagram which would be showing this red and blue falling. So for discussion questions, interpreting the simulation, the intensity for the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicates current flowing in opposite directions. Which colors correspond in the clockwise current as viewed from above and which counterclockwise? How can you know? So we know that the north end points downward into the tube and that the magnetic field points out of the north end and the magnet approaches the loop. Therefore, we know that it has a greater magnetic flux in the downward direction through the loop. And because of this, the induced magnetic field by the loop points in the opposite direction of the change in flux. And the induced current is in the counterclockwise direction. Therefore, red is in the clockwise direction, while blue is the induced, which is in the counterclockwise direction. Second question, what happens to the dynamics of the system when you flip the magnet around? Well, the direction of the induced current would just be clockwise. Nothing else would change. How does the total time in the tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? So, the experimental system was a lot faster than the computational system. And if we want to make a more accurate system, we can calculate the dipole moment, isolate the tube from any interfering magnetic fields, or record the video in slow motion for a more accurate time. Next question, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, when the slope is negative, only the gravitational force is acting on it. And if the slope is 0, the force due to the foil is acting upwards while the gravitational force is acting downwards. What if? So, what if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, the current would increase as there's less opposition. This means that the field created would lead to the bar taking more time to reach the end of the tube. Second question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The current would decrease as the ring's model would not be completed and thus less magnetic force. The bar magnet would have less opposition to the force of gravity and thus reach to the end of the tube faster. Thank you very much. Have a wonderful rest of your day.